just move off. Yeah. I hope all of you have registered your responses. So we'll be telling you about the results at the end in session. We're going to talk about 3D printing softwares and specialized applications, as I told you. So at first, we're going to talk about the ingredients that are required for you to be successful in additive manufacturing. So you require an understanding in design, and you should also be able to understand the software. You should easily be able to convert the 3D machine. Apart from that, you should understand what are the various materials that are available. If you want to move into the metal aerospace industry, so you'd go for maybe titanium. You'd want to learn about titanium material, stainless steel, Inconel, etc. Inconel 718, 625. A wide range of materials are required. So you'd want to understand the material at first. In polymers also, there are a wide range of materials, which we're going to talk about in the later sessions. So a
The
brief
poll results
knowledge
are in.
about this.
Should I publish them so that you can have a look?
Sure.
Just publishing the poll results.
Yeah.
Yeah.
Okay. So as we can see over here, around 40% of you have intermediate knowledge, and around 26% after that are just learning about this technology. You just have a fundamental understanding of designing. So that's good actually. That's why you are in this webinar. You're trying to understand what this technology, about what machine and what processes are available. You need to understand what right kind of equipment that you need to use for the various applications that you are thinking to work on in order to get the desired output. So we're going to talk about why do we actually need softwares in 3D printing. Now, what happens is that you have to design a ultimate goal of 3D printing is to design a 3D model, right? So you go to the design stage. You'll make a 3D model at first. You'll try out. You'll make a 3D model. Let's say, for example, this cube that is present over here. You'll try out different modifications in the design, and then you'll choose one of them after printing. Now what you do is you'd go for certain kinds of simulations. You'd check whether the part that you actually made can withstand various loads, various conditions, etc., that are over there. And you check if your part will actually anchor to the base of your 3D printer well, in case if you are designing supports, etc. Like in this regions over here, you can see it's marked in red. You may want to increase the thickness of this particular regions, because the amount of load that you're applying over there are certain stresses that are present over here. So you do multiple simulations to come up with the right design. And after that, you do slicing. In slicing, what you do is that you take a 3D model and then you cut it into individual layers, individual slices. And each slice is printed by the 3D printer, right? So these slices are converted into G codes, which are printed by the 3D printer. So we're going to focus on each of these steps. So you'll actually be able to understand what all software requirements are there and how you can enter into this industry and learn and progress well. Initially, as I told you, you'd have a CAD file that is a 3D model, and then you'll be doing slicing, as I said. You'll be cutting the slicer will slice the 3D model into individual slices, and that will be converted into the G codes, which your 3D printer will understand and print. Each step in the subsequent slides. Now let's move on to the next poll. Shanko, can you play the next poll question?
Yes, doing that right now.
Yeah. So everyone, the poll question.
Yes, the poll is live right now. I would request everyone to please give in your inputs. Yes, you can continue, Ashish.
Yes. Please register your responses and just press submit. The window will just move.
I will publish the results once we get everyone to respond. Right?
Sure. We'll give a few seconds more for the people to register the responses, and then I'll move on forward. Okay. So now let's move on to the slide. So now we're going to talk about the first stage, that is the pre-processing stage, where you need to understand what is a 3D model. Now,
Okay, I've shared the result. Yes, the full results are in.
Yeah. Okay. So around 48% have intermediate knowledge in computer-aided drawing. Then comes around 18% who have advanced knowledge, and 15% have fundamental awareness. So this major chunk uh, are interested to learn about this in detail, who would want to know the steps in detail. So I'll go move in detail so that everyone gets to understand what this whole process is. So as I told you, actually a 3D model is a digital representation of a three-dimensional object. For example, let's take this Lego block over here. We've got multiple Lego blocks. So you can make a 3D model out of it using a 3D modeling software. I'm going to show you what all softwares are available, how you can start off from the beginning as a beginner and then move to an advanced stage. So once a model is made, you'd actually rotate it along any axis. This is another 3D model that is there. These are various 3D objects that can be made easily. Some of the main 3D beginning 3D softwares that are available for beginners is SketchUp. Sketch is one of the basic softwares that you can actually learn who are not proficient in CAD. Around a lot of them are not. You can start off with SketchUp, start making blocks, and then start joining a lot of components together, doing some basic assemblies, and then start making some complex components like this elliptical gear over here. Now, if you are interested in sculpting, I think a lot of you might not be just interested in making 3D models like this. You'd want to make cool sculptures like this Batman's sculpture that is over here. Then a base software that you can start off with is Sculptrix. And then in case you have to move into a more advanced level software, then you can go for Blender. You can see how realistic these images are. These are some of the softwares that are available for beginners. Next, I'll move on to what advanced softwares are available. Now, once you're proficient with one of these softwares, you can move to the advanced. Like in design, you can learn SolidWorks or CATIA or Siemens NX or Creo. These are all certain advanced 3D modeling softwares. Rather than learning each of these softwares, you can actually learn one for all the mechanical engineers and all those 3D modeling enthusiasts. Software. So you don't have to actually be proficient in it, and then you'll excel. So you look at this model. This looks pretty complex, but as a multiple components over here, each individual component has been finally assembled together, and you can design one individual component using each of these softwares and then finally assemble them together. So this phase that I talked about, after you have made 3D model, made this 3D model over here, you can convert this 3D model into an STL format. Convert a 3D model into an STL format in 3D printing. Now, this surface geometry of a 3D object, convert to STL. Your 3D model, each surface gets converted to individual triangles, and a net of triangles covers it becomes easier. And then now, before moving on to the data preparation part, this is what happens is that you've sliced each of the components into individual layers. I'll show you what all you do in the data preparation portion. What you do is, after you've made the 3D model, you've converted into an STL format, you move on and align your part in an optimized orientation. Now, what is orientation as such? Like, look at this component that is present over here. You can actually move this component in the 3D space. Over here, you can see pitch, roll, yaw, as in you can see the rotations. And then you'd want to orient the part in such a way that you'd minimize supports. And actually, there are, as it is a layer by layer manufacturing process, you could also have certain steps formation as well. So you have to learn how to orient the part in an optimized way. You'd never go for for a cube like structure. You'd never orient your part in such at a certain angle. Because it's a layer by layer process, you'll actually orient it to the base. Like over here, you can see this component. Why would you orient this part and have multiple supports over here, while you can print it in one go in the keeping it at a 90-degree angle? So you need to know how to do the orientation. So that comes with some amount of experience of understanding the file. Now, in data preparation, another thing that happens is that when you have multiple components, now, if you have, let's say, 10 components together, you will not print one component at a time. You'd want to stack them together. Stacking as in, let's take, for example, this octagonal, 3D octagonal structure over here, hexagonal structure. You are putting one part on top. That is what is called as stacking or nesting. But in 3D printing, you'll not exactly put it one part on top. You'll maintain some form of distance in between them, or else the parts will fuse together. So over here, you can see how neatly these parts are nested together. This is in SLS, and this is a headband that is used in face shields. You might be aware of face shields that are being manufactured nowadays. A lot of people are using face shields also. This is a headband of the face shield. You can see how beautifully they've stacked it at a certain distance together. There will be some form of supports in between over here in FDM process. You can easily chip them off. But in SLS, there'll be powder in between each of these components. So around 2 to 2.5 mm distance is maintained in between the parts and in between the bed wall. I'll show you another component. Like, this is another nesting that happens. You are putting multiple components together, and you're printing it layer by layer rather than printing one component at a time. So this is another example of a nesting happening for a metal component over here. You're maintaining around 2 mm gap in between each of them. Over here, you can easily cut them off using wire cut TDM process. A lot of you might not be actually aware of wire cut TDM process. Like in metals, in order to secure the part from the bed, it's directly welded together, joined together. So you use a non-traditional machining process called as wire cut TDM, in which you'll be cutting using a wire cut TDM machine, and then it will cut off the material from the supports and from the bed, and securing each part from the whole 3D printer. Now, in the data preparation stage, there is something known as support generation, as I showed you over here. Now, everything, just like everything on Earth, 3D printing is also limited by gravity. So when you print in processes like FDM, fused deposition modeling, in processes like direct metal laser sintering for metals, supports are generally required. So what happens is gravity plays a role and your part will kind of fall off. So you can see over here a simple example, this T component. Now, if you try to print it in one go, you can see that the part will actually fall off from this portion. So you want to anchor the part to the base so that it remains as one single component. And later on, you can easily remove off these support structures. You can see over here, this kind of a L-shaped component at a certain, you have to, at a certain angle, let's say 25 degrees from the base. If you don't provide supports, it will break off like this. You can see over here. So support generation is actually very important. And slowly and gradually, when you move into learning about the software, etc., later on, you'll learn how to generate supports. Um, and it's not a very difficult process. Easily you can learn. You just have to follow certain thumb rules, as I've shown over here, say at an angle of 60 degrees. You have to be sure that there are supports. So you'd never actually fail. Over here, you can see certain components. This is a proper failure due to lack of supports. So you should make sure that you have the best orientation for your part. You have to, or else you'll actually spend a lot of time in post processing. I'll show you a part later on. Now, this is another support that is generated in Magic software. I'll show you the part in the next slide. So what happens is that you'd be using certain simulation softwares to be able to understand. Like over here, you can see this region, it is marked in red. You actually require some form of supports because gravity is playing a role, and the part will actually fall off during the printing process. So this is the same part that you can see over here with the support structures. And then using Wirecut EDM, as I said, you'll cut off the support structures from this part and secure the final part. This is one of the parts that we made for ISRO. And you can see the part is easily secured to the base. So this is the actual 3D model of the part. And then you cut it off and then you get the final product. Now, in the data preparation stage, slicing is another requirement that you need to do. As I said before, you have to, the 3D model is sliced into individual slices, as you can see over here. Let's say, take for example, this 3D, this diamond object. It is cut into individual slices. Now, what are these slices? You're saying, I mean, slicing. What are these slices? Slices are actually, what happens is that slicing turns this 3D model into G codes. Now, what are G codes? G codes is actually a control language. It's actually like a programming language in which you'll tell the 3D printer from where to start and from where to end. From where to start and from where to end. So you'll be specifying the movements of your extruder head in this case. So the 3D printer will get to know from where it should start and move on in a linear fashion or whatever is the geometry and make the component. So once the first layer is made, the first G code is supplied and it makes the first layer, second layer, third layer, fourth layer. Like that, individual layers are laid and then you get the final object. And in slicing softwares, there are multiple softwares that are actually available. Slicer 3D is one of the basic softwares that are there. Then if you want to, if you want to move into, let's say, more advanced softwares in slicing, then you can go, you start using Materialize Magic, Autodesk NetFab, Ultimator, Cura, Idea Maker, Race 3D Idea Maker. This is one of the new softwares that are there. So this is how you go about slicing. Over here, as I explained to you, this as the 3D model looks like this. After you make the STL file, you slice the components into individual G-code layers. Yeah, you can easily see how the slicing is done. This is a completely uniform slicing. Over here, you can over here non-uniform slicing is there. Then uniformly you slice, and then non-uniform slicing, depending on your parts, etc. So slicing is absolutely important in all 3D printing technologies. So one of the main reasons is that once you slice, each layer thickness will, let's say it's 100 micron for one slice. So this is how the surface finish will actually look like. And in case if you go for something like 10 micron, the surface finish will look something like this, but you'll be actually compromising on your print time. So for 10 microns, the 3D printer will make the first slice. Then after 10 microns, that is a very small distance, it will make the second slice, then another 10 microns, third slice, like that, multiple. So you take around 80 minutes to print this whole component. Now, in case if you have a layer thickness of 100 micron, so first slice has been made, then at a larger distance, you make the second slice, then at another larger distance of 100 micron, you make the third slice, like that, multiple slices you make, and then you're actually spending only 30 minutes. Now, you would actually optimize your slicing in such a way, let's say take 50 to 60 micron for this part, and then make a part with a better finish. And then you can do some form of post processing, as I had mentioned in the previous webinar. You can actually sand this component, and then you can actually use it. Now let's play the next poll. Shanko, can you play the next poll question?
Yes. The third poll will be live right now. I would request everyone to kindly give in your answers. Yeah, it's live.
So FEA as in finite element analysis, FEA simulation.
Yeah, so the polling is going on right now. Just give a couple of seconds. We will get the results immediately and I'll publish it. Right?
Sure. Please register in your responses. Don't worry. After you register it, press submit, and the screen will just go off. I'll give you a few more seconds so that you can register your responses.
Yes, we have done almost. 90% of them have voted. So should I publish the results?
We'll wait for a few more seconds. Maybe some of them might be still working. Okay. What do you say?
Sure. Yes.
Yeah. Okay. We'll wait for a few more seconds in case if people have not registered their responses.
Yes. Did you publish?
Yeah. Sure.
Yes.
Okay. So as we can see over here, around 36%, majority of you have used FEA simulation softwares in your lab or universities. And after that, a major chunk have actually read about FEA simulations, etc. And around 28% are not aware of it. And only a small percentage are experts in finite element analysis simulation softwares. So
you can go by depth with it, right? The FEA.
Yeah. So yes, slowly we can actually move into depth of it, and you can learn more. So
okay. So let me end the result. You can continue with the presentation.
Yeah. Okay. Done. Yeah. Okay. I'll move on to the next slide. So as most of you are not actually aware about what is finite element analysis, I'll try to give you a small brief introduction of what that is. It is actually the most widely used method for actually solving problems in of engineering and mathematical models. So typical problems that are there are, for example, these components that are present, this component that is over here. What you do is after triangulation, you'd you can see over here that there are certain you apply the loads, boundary conditions as they call it. You apply certain boundary conditions as you know that this part is going to be used in a particular application. You are aware of what loads, what heat conditions that part is going to go through. So using FEA softwares, you simulate that particular environment for the part, that particular environment in the virtual space. So for that, you'll be using FEA softwares. There are a wide range of softwares available. So you'd want to start learning by one. I'll show you certain softwares that are available. As a lot of you are beginners, you'd want to know about it, want to learn about it. So this is one simulation that you can see over here. uh, Over here you can see in the red zone there is a lot of, as you've applied all the load conditions, etc. This is actually a thermal stress concentration what to say simulation. Over here certain heat, you can see certain the thermal heat concentration is higher in this region, so you'd actually provide more insulation in that region, etc. So in 3D printing context, let's say if this simulation was for supports, I'll show you in the next slides. Like for supports, you'll get to know that uh, where you have to put the supports, etc. If you are lacking in areas where you want to put supports, so that the simulation will tell you that the part is not anchored properly to the base. So simulation will give you the imitation of the process operation that is going to happen at the end. So you'd actually be able to avoid printing failures. You'll be able to optimize your production, and before the printing process itself, you'll be able to find out the probability of failure. You'll get to know if your part will fail or not. So before going for the final printing process, you are advised to go for a simulation process. So you'd not you'd actually prevent any risk during the printing process, because you are, in case if you're starting your own company, you don't want to have a lot of failures. I mean, you'll definitely have a lot of failures, but you'd want to prevent that. So simulation softwares help in that. So these are some of the FEA softwares that are available. In this case, we'll talk about supports. We've ANSYS, we've got Simifact, we've got Additive Flow, Atlas, etc. You can start off with learning maybe ANSYS or Simifact like that, or maybe Additive Flow. Use any one software and become an expert at it. At Objectify, we use Simifact, which is a very good software. It helps us understand the printing process before it actually happens. So you are able to simulate the support generation and understand the temperature distribution, etc., and the forces that are being applied before the printing process. These are a few of the new softwares that are there, Additive Flow, etc. So start off by learning one of the softwares, then advance one by one. Maybe if you feel that this software is not so user friendly, A, B, C, D, whatever be it, go for the other software. Try and learn in detail. Go and learn using certain what to say online courses that are available, etc. LinkedIn Learning has a lot of good courses that are available, and advance in your field. Over here, you can see this GIF image. This is a simulation that is being done in this software, Simifact. You can see this region, which is marked in red. You can see that you actually require supports in that structure so that the part does not fall off due to gravity. This is another simulation that is there. Certain red regions, you'd want to avoid this. Now, as we are advancing into the future. So certain softwares that are actually available to automate your whole process. Some of these softwares are called ERP softwares, or enterprise resource planning softwares. What happens is that you are able to automate the whole process that is going on. For example, let's say, for example, you have a 3D printing service. You have your own company. Now, a customer comes to your website and he decides that he wants to print this particular component. Let's say a cube. He wants to print a cube. So he comes to your website, and then using these softwares, the customer will upload the 3D model, and using these softwares, it will actually generate an automatic auto generate quotes, etc. And then it will once the quote is generated, when the customer says, okay, I'm ready to, the pricing is good, can I start printing? So he'll give an update that he wants us to start printing. So then in the next process, a queue, the first part will be sent to the manufacturer, and then there'll be multiple projects which will be queued one on top of the other. And then one by one, we can start printing, we can update in the software, and the customer will get a response. The whole supply chain, etc., is automated in one space. So these are some of the commonly used ERP softwares in 3D printing: Link 3D, PrintSys, 3D or Mind, and you can actually learn about these softwares also later on. In case if you are not actually interested in the 3D modeling part or the mechanical part, you can actually learn these things, how they're doing it. Maybe you could all design a ERP software for 3D printers, indigenously design a 3D ERP software for India, for 3D printing companies in India. In case if you are a coder, you have good coding skills, go ahead and do that. That's what people want in this industry. Now, this is how the workflow goes about. I'll not move in detail, as I've mostly explained most of it. Now, now there are a lot of quality assurance softwares as well. So what happens is that you collect the raw data of the part, etc. There are a lot of quality metrics, etc., that are present, and you can actually be able to report what is happening in each layer during the printing process. As I've explained, each slices, right? Each layer, you can get to know what is happening in each of this, each of the printing process. Is it in an optimized way? You can actually be able to reduce the production cost and do a very good real-time monitoring and analysis, and get a very good feedback from the software using such quality assurance of softwares that are provided by Sigma Labs. So talking about certain specialized applications, in the previous webinar, I'd shown you some exciting applications. Here I'd move into more specialized applications. Like over here, you can see this insert component that is being made. When you see it from here, sitting over here, you'd see this as a simple block. But no, there are actually helical channels that are present inside. You move the part, and then you can see there are two holes present inside, through which you can actually flow in the coolant, etc., to cool the component. So such difficult to make designs are actually possible using additive manufacturing processes, and that is how the industry is advancing right now. Another interesting application that we have is topology optimization. So what happens is that in certain components, like you can see this component over here, this is for a part made by GE. You can see that when you use traditional manufacturing processes or subtractive manufacturing processes, as I had explained before, you take a block and then you machine it, and then you make the whole final component over here. Now, this is how the final component will be achieved. Now, what could you do using additive manufacturing processes? Using topology optimization, you can actually remove the material from these areas for the loads and conditions that are applied. You know that you will be applying, let's say, 5 Newton force over here, 10 Newton over here, whatever be the forces that you're going to apply. So you don't actually require so much material. Now, using this technique, topology optimization, you can remove the material from this component, and then you can have multiple designs. You can validate the design and then come up with the final product. So one of the examples that you can see over here is that of a seed base over here. Most of you have seen seed bases, etc. You don't actually require a lot of material over there. Now, this is a topologically optimized design. You can see how much material they've saved over here. This is actually a very like a block structure over here. And then finally, you can put the cushions on top. So you're saving so much material and you're saving time. And this is only possible, the manufacturing such a component is only possible using additive manufacturing process, not traditional processes. Such machining such areas is very difficult, and it's actually not possible. Now, some of the specialized applications is bioprinting, as you can see. A lot of companies in the United States have started coming up with something called as bioprinting. Now, in bioprinting, what you do is you can actually print tissues, organs. This is an organ on a chip. Can you imagine? This is actually manufactured in Harvard. This is an organ on a chip. So they've simulated this component, and they've seen how there are multiple channels also present inside. So fluid can actually flow through in this. And you can see a heart that is 3D printed over here. I'll actually show you a video to give you an example of 3D bioprinting. What they do over there. So just to give you a brief before that video, what happens is that in this model itself, there are a lot of supports also present inside. Those are also proper tissues, human tissues that are printed. So you can imagine in the future, in case if you, God forbid, it doesn't happen, but if something like that happens, you want to have an organ donor, you can actually print an organ and directly use it. So you don't have to wait months before an organ donor comes up in the queue. So this is a revolutionary technology. This is a 3D, a 6-axis 3D bioprinting machine. You can see there's printing a spine over here. This is the process. You can see they're making veins over here. They're making the skull component. This is a cranial implant, as I'd shown in the previous webinar. So this is how you can actually do bioprinting. There are multiple multiple tissue layers that are poured in layer by layer, and you get the final part just the same as you do in FDM. But over here you've got you can see this printer over here. You've got multiple scaffolding, liquid polymers, liquid tissues, etc. A lot of things are actually involved. This is actually still in developmental stage. So, and you can also 3D print sand. Yes, you heard it right. You could actually 3D print sand also. This is a sand 3D printer, but the applications are pretty limited. They have advanced in this field, but slowly in various castings, etc. They are actually they are slowly adopting this. You can also print composite materials also. This is one of the composite 3D printers that are available. These are certain composite materials. You can actually print carbon fibers, etc. A lot of other composites that are available. Certain machine manufacturers have started manufacturing these printers, etc. This is a Venn diagram of various softwares that are there. I've mentioned only a few basic softwares that you can learn, but these companies like Dassault Systems provide solutions for CAD, computer-aided engineering, as I said, ERP, as I had explained, and there are wide range of other software makers as well who work in the 3D printing software industry, like Desktop Metal, etc. Altair HyperWorks is another major player in this. We've got Simufact, Ansys, Additive Flow, a lot of them. So this is a Venn diagram to show you various softwares, etc. Now we'll have another poll, which will be the last poll, and then we're going to end this session. So please register in your responses. So, Shankuk, can you please play the poll before we end this session?
Yes, the poll is live right now. This is just your overview of how much you like the session, and we will be bringing in more. We have 3 more webinars to go, and we hope by the end of that you will be completely aware of the 3D printing technology and how it functions. The next webinar will be on the various materials that are used in 3D printing. We have seen a lot of questions coming in on the type of materials, filament resins, and everything. So we'll be discussing that in the next webinar. Also, we'll be giving a summary of what is 3D printing in the next webinar as well, so that even if you have missed the previous webinars, you can catch up really soon. So yes, Ashish, you can continue with the presentation. We have got all results, and yes,
Okay.
we can move into Q&A section, I believe.
We were actually ended with the presentation. So we'll now slowly move into the question and answer session. We're going to answer some of the questions that are being asked over here, some prominent questions, some interesting questions. I can see there are a lot of questions being asked by people out here. And we've answered around 50, and 11 open questions are still there. So, okay, so let's see some software. Okay, can you tell us on 4D printing technology? Okay, so what in 4D printing technology, what you actually do is these are self organizing structures. So you actually 3D print a component and use, let's say, water, let's say heat as a media to which will be the third dimension. And time will be the third dimension. You actually use heat or water as a media to self self-organize the part into the final component. So there are a lot of research labs in MIT, etc., which are actually working on self-organized parts, which convert themselves into the final product automatically over time. So time is the fourth dimension. So I've answered the next question also. What is the difference between 3D and 4D? Over here, the time is the fourth dimension. So who is using 4D technology, OEM suppliers globally? Nowadays, actually, this is still in a developmental stage. So people have started researching on it. If you're very interested in this topic, then you can follow Mr. Skylar Tibbets. He's part of the MIT lab for self-organizing structures. And he is involved in this in this 3D printing process. So hope I've answered that question. Now next, how much
time? Ashish,
yeah.
Do you want me to take a couple of questions as well?
Yeah, sure. Why not? You can also take in some questions.
Hi everyone, my name is Rahul Pise. I'm a general manager for design and operations in Objectify. So let me answer some of the questions live. So I had answered quite some of interesting questions, up to 30 questions I have answered so far in a text format, but I felt some of the questions I should take it live for the benefit of audience, and I felt compelled to answer them live. So some of them are very basic, some of them are advanced type of questions or very specific type of questions. So let me begin with the very basic one. So people are asking about the file formats and what is this file conversion business you are talking about. So as you might know, in case of manufacturing industry, you need certain level of detail of information for machines to automate the movements of uh, the mechanization in order to do certain objectivation. So in case of age-old technologies which are very matured, like die casting or forging or any sort of injection molding type of industry, you prepare a mold and it is basically doing automated movement for pressing and ejection in order to first press so that the cavity is tightly bound and you fill in the material in those cavities and then you remove it. So it's very simple mechanized operation. But in case of CNC machines, it has to take the cutter as per the profile of the parts. So that's a numeric control, but on top of that, computer numeric control. So in order to generate that data, how to trace that specific path, you need to make a numerical data that you need to move in XY direction this much, Y direction this much. So there had been a translation happening in background on those sort of automated machines, and that is using the product design data to begin with. So you need a robust product design data where the accuracy and precision is such that you feed that data to these automated machines and you get the resulting components processed. So CNC technology and all these previous manufacturing technologies are very matured. Similarly, in case of 3D printing industry, stereolithography triangles, that sort of tessellation data is very matured as well. So people had been asking while converting into STL files, but precise curve will not be exactly converted into triangle format for STL file. So there had been certain approximation standards anyway in case of 3D printing, or CNC machining as well. So how much interpolation you can do based on that, what is the degree of accuracy for the travel bed will be dictated. So in case of CNC machine, if you are having a coordinated 3-axis machine or 5-axis machines, all those individual axes, if you are going to get the positional accuracy in the range of 25 micron for coarser machines, then your geometry accuracy that you print, that you process on using CNC machines will be up to that. So similarly, in case of 3D printing as well, there is a approximation essential because you have a process where it is depositing layer and layer upon layer. So how much layer thickness that you can achieve will dictate the quality of the component as well as the resolution and what is the stair stepping effect that you get. So the STL file is a crucial key so that you can get a smoother and well-defined geometry, but the degree of accuracy you can choose. So how much finer you want will be depending on the process that you are using. So there is a very robust algorithms written for stereolithography triangle files, and it can go for a very fine accuracies as well up to sub-micron level, but the file sizes will become very heavy. So the standard practice in the industry, we use 10 micron as accuracy for a layer thickness of up to 50 micron, let us say. So I think I answered for the STL file preciseness. So there is another question.
Sir, can I interject for a moment?
Yes.
Yes. So I would like to also make you aware that in this presentation, we have talked about two specialized processes. One is conformal cooling and the other is topology optimization. If you would like to know more about any in depth about those two processes, we have actually made a webinar series in the past, and you can find that in our webinar section in our website, where the video is where the video on demand is available. Kindly go there and watch those videos to clarify any doubts regarding conformal cooling or topology optimization. Yes, sir, you can continue.
Thank you, Sankar. So you can refer to the previous webinar series as per specific topics. So some of the professional advanced type of topics we had discussed in past webinars, and some of the basics as well we had discussed in uh, innovators at home, but that was with the intention of mostly creating a content for professional people already in the industry and not for the academics or students. So in this series, we are addressing your tryst of learning this technology, and we are a little bit patient and going through details one by one. And it's the content wise, it's more broad based and academic kind. So let me answer some of the questions which were I was supposed to answer. So let me answer another question. What is the difference between STL, 3MF and AMF formats? So all these formats are efforts in order to elevate the game. So stereolithography triangles is just triangulated tessellated data where what you can get is 3 points on the surface making a triangle tessellation. For each triangle you get a vertex as well as normal, and the normal will define the orientation of that specific triangle and surface. So how the surface is oriented, that is only, so it's very basic data. It doesn't give information about how the properties are varying over a geometry, or how the attribution of specific features on those geometries are. So feature-based modeling or parametric modeling is a very easy for engineers and designers to alter certain features and all. So once you convert to STL, going back and editing is much tedious. You can do it only using the CAD modeling softwares. But people are looking for software packages and the file formats where they can do last minute editing as well. That's why one format called 3MF is being developed, where you can edit certain features at the last moment. And AMF format is another similar sort of approach. And on top of that, I mentioned it's elevating the game. So the strategy behind it is not just giving the empty shell type of data, but how the construct of a geometry should be inside as well as on the surface in terms of textures, colors, that can be achieved via 3D printing technologies. And there had been a lot of process planning issues and communication gaps that people have observed, and that's what this effort is going forward to establish certain file transfer format. Ultimately, all these files are writing certain scripted information about geometry that you want to process in a very standardized and a robust fashion, so that the machine can read it and process it as needed. Okay. Then there are few questions that I have seen. In case of metal material, uh, can we give support for inclined surfaces because it's difficult to remove extra metal? So the question is from Rakesh TS. So what he's asking is about why support structure is essential in first place for metal versus polymer, and why uh, we try to avoid giving support on certain inclined surfaces because it is difficult to remove or something like that. So let me answer that question. So first of all, support structures are needed in very few specific technologies. Not all technologies demand it. Mostly the powder bed fusion of a nylon type of polymer, you don't need support in that. It is self-supporting and you can print it without support considerations. But in case of stereolithography, fused deposition modeling, and in case of metal, the support generation becomes very key. The reason behind it is the geometry will collapse if there are no supports provided. So support is in order to deposit the next layer and giving a firm uh, base for the subsequent layer is essential for few technologies. But in case of metal structures, it is even more essential. It's providing a support, that's the first thing. But on top of that, it has to remove the heat from the body, because compared to polymer, the temperatures at which metal melts is quite high. And in order to dissipate that heat from the uh, part body or the zone at which you are exposing the uh, power beam, maybe it is a laser or a electron beam, that heat needs to be dissipated after melting. So otherwise it will accumulate and simply have a burn marks or distort the geometry very severely. In order to get the superior surface finish as well as superior accuracy, you need to dissipate that heat very robustly, and that's why the support play a very important role. So how you design that will result into a better quality of a geometry with the accuracy and precision. Okay.
Sir, can I actually answer one question? One interesting question came in.
Yeah.
And it was actually pretty good actually. How can we use, as a civil engineer, how can we actually use 3D printing as a technology in concrete 3D printing? So a lot of companies out there are actually using concrete 3D printing. So what they do is that they push the material through a nozzle, as we do in FDM, as you can see over here, we explained. And they make it layer by layer to print buildings in 3D. They can actually build walls, frames, various building units as well. And a lot of research is also going on in building, in manufacturing bridges as well. If you're actually very much interested in this topic, you can actually go and refer some companies like Cobord and CONCR 3DE. You can actually go and learn about those companies. Sika is another company out there. So it is another interesting topic. As a civil engineer, you'd actually love it. And as one of few examples that are there, check out that Dubai municipality building that was 3D printed. And a lot of buildings in Netherlands are also being 3D printed now by certain companies like Cobord. So please check that also.
Okay, so one last question I will answer, and then we can wrap up the session. So, Ashish, can you go back to that Venn diagram of all the softwares? Ashish?
Yes.
Well, that Venn diagram, Ashish will flash soon. So what context of that and what was the question? I will briefly have a uh, at least question stated for audience. So the question was, which is the best software out there for 3D printing? As any novice or new to these terminologies and lot of softwares and lot of players, anybody can get confused. Anybody will ask, what is the best deal out there? What can I get? So it depends, depending on what you are looking for and in what context of industry or problem solving or product development or services that you are seeking those softwares. So you see, it's a huge ocean of number of players and software developers and the specific segments or specific needs of the industry they are solving. So right from part design preparations that are based on computer aided design mindset. So these are the software agencies who develop parametric or feature-based modeling methods where you can define certain features uh, and construct a geometry or a body. And that data had been a norm for conventional technologies and being adopted by manufacturing industry for more than 4 decades. So it's very robust, and the major players starting from Autodesk. So they first launched AutoCAD, and it is adopted not only by mechanical industry but civil engineers. Although not just civil engineers and engineers, some of the companies who are just making fabric design and they are cutting layouts of our shirts and trousers robustly and at a manufacturing scale faster. So it's not by manual scissors or cutters. It is using laser beams and they cut out the layouts. So 2D design was the first norm for design industry. Then it became a 3D because of the computer graphics. And now you can design almost from a just a very tiny paper clip to fighter jet uh, or a carrier vessel for navy or something of that sort, or even buildings, construction industry, uh, any sort of product that you can imagine a shape for, you can draft it using CAD modeling software. Then how that CAD data, which is just a geometric representation using certain mathematical basics and kernels behind it, how that can be converted into something that you can manufacture, that is computer aided manufacturing. It's again a very huge discipline in itself, and major players in case of slightly older technology on top of which this technology is evolving. So the precursor of 3D printing technology is the CNC, computer numeric control. And in that realm, they had popular names like Mastercam, Delcam. So those CAM softwares used to convert that STL data into numerical codes or path planning for certain cutters. So similarly, in case of 3D printing, instead of cutter planning or tool path planning, what you need to do is how your laser is traversing, or how your extruder is traversing, or how the binder jet uh, has to cover certain specific areas, or in case of polyjet, what cross-sectional area those nozzle need to do the droplet fill. So all that sort of nuances are taken care by the CAM software. So popular names are by Autodesk, Netfab, or Materialize Magics, and there are huge number of players in this segment as well. Then how you manage the workflow, process plan. There are another island of players working in that area, ERP softwares, where it helps the service bureaus or bigger manufacturing units to do the sequencing and planning of which objects to be printed in sequence. Then quality is another area where you can do 3D scanning or CMM of the outcome parts. So there are again number of players, and simulation is a big computer-aided engineering discipline in itself. So there are a huge number of players, and few prominent names you might have heard, like ANSYS, and from Dassault System, uh, Abacus, or Altair. These are the popular players who had developed this type of CAE softwares. And ultimately, what people are looking for, if you are looking for a best deal, you should be looking for the sweet spot of these Venn diagrams, where it encompasses all the disciplines and still serves your needs. So it depends on what are the services and solutions you are looking for. So most of the island these companies are covering as an integrator. So you can choose one of that. So I hope answered the core topic of today, and giving you a flavor of how many players there are. There is a explosion of software industry going on in this space, because every day people are learning, developing new technologies, advancing it further, and pushing the envelope and creating solutions around it. So but few prominent names I mentioned. So I think now it's 6:10, close to 10 minutes overtime. So I hope we covered curiosity on software front, and I leave it to Sankha and Ashish to wrap up and close off. Thank you.
Hello. Hello.
Yes, Ashish, we should wrap it up right now.
Yeah. Okay. So we'll wrap it up. So thank you all for attending today's session. Next will be on materials used in 3D printing, powders, filament, resin, etc., and how to use 3D AM materials. So Shanko, any last?
Yes, yes. Thank you, Ashish. Thank you everyone for joining in. This was part 2 of the 5-part series we are having for this month. I would request everyone to kindly pitch in for the next webinar. Even if you missed the previous webinar, don't worry. We'll be sending you a webinar bundle, and as along with the presentation, and as well as the videos. Thank you everyone for joining in. Thank you, Rahul sir, for your valuable feedback. Thank you, Think Create 3D, for your support. And we would love for everyone to see, kindly pitch in all your friends and everyone who is into engineering, who is a little bit knack for 3D printing and would love to know more about it. Let the word reach us as well, and meet us in the next sessions. Thank you so much. Have a nice evening, and bye-bye.
Bye-bye. See.